Hello, everyone. Let's get started. We are going to continue with the linear regression today. Last time I think in class, we have looked at the nature's bar to see, how we can interpret the basic results from Radiant when actually run the linear regression. And also, we have looked at what kind of things we have to do before we actually run a linear regression. We have to check the plots, right? We have to check the distribution of data, and also we have to check the scatter plot so that we can see what kind of signs will be actually derived when you run the regression between x and y, right? So y is basically uh, the result of all of the things, the impact is kind of made on the y, right? And x is basically, all the different kind of things that may impact the y. In that sense, x is basically, for instance, if you think of, what kind of things will impact the company's profits, and then maybe the price, cost, and then computers price, computers cost, and the income amount of the people, in certain areas, something like that. All of these things will impact the profit or the revenue of the company. So in the case, we may try to predict what kind of revenue or profit we are going to have when you actually have some different amounts of the prices, costs, and etc. Okay, so today, we are going to look at this in detail. By explaining uh, the basic procedures, behind the linear regression. And also, I'm going to provide some theoretical explanation behind it. Okay, let's start. So let me actually share the lecture note. Okay, we have used the nature, the data set, and then it has the y variable, the sales, and then it has advertising promotions and the computer sales and the snowball, right? So when you first look at, for instance, the scatter plot, we kind of see that there's some positive relation between sales and advertising and sales and promotions, and the negative relation between sales and computer sales, right? Again, later we are going to see if we don't check these things before, then sometimes we cannot recognize the problem, especially that comes from multicollinearity. So basically, when there are some correlations among the x variables, the signs actually in front of them, actually the coefficient signs can be different from what we can expect. Unless we check this, we may not recognize it. We have to check the distribution and then scatter plots. As we have looked at last time, these signs make sense here, right? Because if you put more money on advertising or more money on promotions, then sales are expected to increase, right? Also, it's pretty natural that if computer sales increases and my own sales will go down. These signs make sense. So when you run the regression in Radiant, as you can see, we as a response variable, we have basically designate the sales, right? As you can see here. Right, let me actually change the pointer to actually the pen. And then, so this is a y, right? And these are all the x values, right? What know is that snowfall is not actually not relevant, but even before that, let's say we have selected only these three variables, and then when you run the linear regression, then let's see how we can interpret these things on this screen. So first, First thing that you have to check is this R square value. So this is basically about the whole model. And these actually for the individual exploratory variable, so individual X, okay? So first, let's look at the coefficient in front of advertising, promotions, and the computer sales. Oh, by the way, I mean, we have coefficient as the intercept. Um, I think, I mean, for the time being, I mean, don't worry about this coefficient. I mean, it's just the intercept, okay? That's enough. So, as I explained in I think the first class, in the last week, I mean, regarding the linear regression. So for the linear regression, what I assume is that, okay, the y, in this case, the sales, is a function of all the xi's in a linear way. So beta 0 plus beta 1, x1, up to beta, let's say k, xk, and we have some errors that cannot be explained by this linear model, right? So we don't know what beta 0 is. We don't know what beta 1 is and up to beta k. I mean, if we know, then I mean, we can uh, easily predict what sales we can have. I mean, if given value of advertising, promotions, and computer sales. But anyway, so by running the linear regression, what the actually program is doing is they estimate these beta 0, beta 1, beta k using sample data. So in this sense, I mean, B0, B1, Bk are called as estimates of the true parameters, beta 0, beta 1, and beta k. Okay. So in this case, I mean, this is the B0. 65.705. This is the B1 for the advertising. This is the B2 for the promotions. This is the B3. So as expected by the scatter plot, the B1, B2, they are positive and the B3 are negative. So at least, I mean, they kind of coincide with our initial investigation using the scatter plot. So when you look at the null and alternative hypothesis, the null is that the effect of X on sales is zero. So it means that basically all the beta i's, I mean from beta 1, beta 2, and up to, in this case, I'm actually the k is equal to 3. So let me just write down beta 3 is 0, but for in general, beta k is equal to 0. And then the alternative is the kind of the opposite of the null. So sorry. So it means that either beta 1 is different from 0, or beta 2 is different from 0, or beta 3 is different from 0. Okay. Just to make sure, maybe let's actually erase it. So basically beta 3 is 0. Okay, perfect. So I think I have actually explained this already in class, but just to make sure that I'm just actually going through this again, okay? So B0, B1, Bk estimates, and also it turns out that expected value of Bi's is actually the same as beta high. In that sense, I mean, Bi is also is called as an unbiased estimator. So we have this. I mean, so these, I mean, how we can interpret these results, right? So for instance, I mean, if we look at, let's say, the computer sales, and if there is a $1 million increase in computer sales, and then we expect that the sales will decrease by $1.8 million, keeping all S is constant. Actually, these are actually the very, very important parts. When you look at the estimates of these beta i's, The basic interpretation makes sense only when that particular thing is changing. Okay. So for instance, B1 is about advertising. So if there's 1 million increase in advertising, then we are going to expect that the sales will increase by $49 million. But at this time, all the other things like basically the promotions and the computer sales, all of these must be the same. Okay. Okay, so hold on a second. Let me actually change the winner. Okay, so and also, I mean, let's look at the how we can actually interpret the ice curves. Okay, so if you look at the in the left panel, I mean, of the regression, you can actually check the sum of squares, and then you can see the details regarding the sum of squares. And then the first one is the regression, and then error and the total. So total is basically the total sum of squares, and then SSE stands for sum of squared errors, and then SSR is basically sum of squares regression. So you may wonder that what that is, and then basically the total sum of squares is about what is the square difference between the observed value and then the predicted value. Okay, and then sum of squared errors is basically the actual value and then predicted value. So we are looking at the difference and then the square and then taking the sum. That's the sum of squared errors. So anyway, for the time being, I mean, let's you can just think of um, total sum of squares is kind of a total deviation, okay, and then sum of squares regression is basically is the error, not the error. I mean, it's the kind of deviation because of the um, regression, okay. I mean, for the exact thing, the explanation, let me actually go to this slide. I think, oh, okay, because I skipped this part, but uh, maybe you may want to see this one. I'm sorry. Oops. Mhm. This one, not this one actually. Let's look at the yes, here. Okay, I may have to correct. I think I need to correct my first explanation regarding the total sum of squares. So total sum of squares is basically the as you can see, is the observed value and then the average of the sales. So when it comes to the sales data, the YI is the individual sales value, Y bar is the average sales, and then we look at that the degree of variation from the mean for the sales. That's basically the total sum of squares. So you can think of it like a total deviation. And then SSR is basically sum of squares due to regression. It means that um, the reason why it's different from the average of sales is because I mean, some of the X variables are different. So basically, for instance, I mean, if we, because we have put more money on advertising or more money on promotions, so that why I had, for instance, is somehow higher than the average sales. So in that case, I mean, taking the difference between the average sales and then y I had, which is predicted sales, and then we just square it, and then taking the sum basically is the part of deviation that can be explained by this model. And then if you look at the sum of squared errors, and then this is actually the difference between the actual observation and then the predicted value by the regression model. So it means that even though we have incorporated the effect of advertising, promotion, computer sales on this sales, but still there's something that cannot be explained by this model. And that's actually captured by this point. So sum of squared errors. Okay. So when you say that a particular model, linear regression model is good, it means that basically sum of squared errors is small, right? In other words, I mean, sum of squares regression is large. Okay. And as a kind of as a basically some kind of coefficient that determine whether this linear regression model is okay or the good in explaining the deviation in sales, we are using uh, some value that is captured by the ratio of SSR and SST, and it's called basically the R-square value. So R-square value is basically SSR, sorry, SSR, SSR. So deviation that can be explained by the linear regression model divided by the total deviation. So let's say if R-square value is 0.8, it means that 80% of deviation. So here the deviation means that um, the deviation from the mean. So it's kind of similar to the concept of variance, right? So variance is basically the measure of dispersion. In a similar way, the total sum of squares is basically a degree of dispersion around the sales. Okay, why for some area the sales is higher than the average sales or lower than the average sales? Okay. And then some of those kind of things can be explained by advertising, promotion, and computer sales that's captured by SSR. So R square value is always between 0 and 1. So, and obviously as R square is getting bigger and bigger and close to 1, it means that almost all part of deviation can be explained by this model. Okay. So, okay, let's make you go back to the slide that we were doing. So let's go to let me see. Yes, I think this part. Okay. Okay, maybe the previous one. Yes. So coefficient of determination R square is basically how much it kind of indicates how much of the variation can be explained. So in this case, R-square value is 0.833, so which means that 83.3% of the variation in sales can be explained by this model. And that is calculated using the ratio between explained deviation SSR and the total deviation. Okay. So let's look at let's try to have some kind of uh, guess on how it looks like when with certain R-square value. So if R-square value is equal to 1, it means that any variation in Y, all of the variation in Y can be explained by the X. Okay, so basically, if you know X and if you're going to know Y, that's the meaning of the R-square value of 1. If R-square value is equal to 0, it means that it doesn't explain anything about the deviation. So regardless of X values, and whether it's X is small or large, we are going to have a similar pattern of variation. And then it's basically R-square value is 0. If we have a 0.8, it means that, as you can see here, there are some values, some are quite close to the linear line, but there are a few, several actually in this case. There are somehow a little bit far from the the dotted line. So here the dotted line, you can think of it as actually the regressed equation. So this is actually the y hat. Okay, so so basically this is the y hat. Sorry, this the dotted line is the y hat. So predicted sales. Okay, in the example that we are looking at. Okay. And then 40% means that, as you can see, there are more values, more points that are somehow far from the regressed equation, right? For simple linear regression, where we have only x, R-square value turns out to be the same as the correlation coefficient squared value. So this is actually somehow some different data set. I mean, correlation example data set. And then as a response variable y 0.4 and the explorative variable x 0.4, only one x. And then in that case, if you run the linear regression, then R-square value is exactly 40%. And if you check actually correlation between x and y, it's actually 0.63. Okay, so if you square it, that's the same as the R-square. So which means that if you have only one x, I mean, basically for simple linear regression, even without running the linear regression formally, you kind of see that the value of R-square by just squaring the correlation coefficient row. Okay. So if you go to the correlation menu, and then you can see that the correlation is exactly 0.63. The next thing that you need to understand is the adjusted R-square value. So in this case, 0.78, seven, sorry. That is somehow less than R-square value, okay? I mean, that's always true. I mean, always adjusted R-square value is less than the R-square value. And the reason is that because, I mean, adjusted R-square value, it has this form. So 1 minus sum of standard error divided by n minus k minus 1. So you may wonder that what is the n minus k minus 1? So here, n is number of observations. So basically the sample size n, and k is basically number of x variables. In this example, I mean, we have a k is equal to 3. So, and the number of observations is actually, you can see the 15. So it means that the 15 minus 3, 15 minus 3, and then minus 1. So the degrees of freedom for the sum of squared errors, that's actually this value. So this 11 is actually the here, n minus k minus 1. Okay. So this is basically degrees of freedom, so 11, right? And then the sum of squares is also divided by n minus 1. That's the degrees of freedom for this, the total sum of squares, and then 14. So when you calculate, so this is 0.78 same. And then why this is always less than R-square value? Because the regular R-square value is SSR divided by SST. This is same as 1 minus SSE and SST, right? But if you look at the difference between these two, then you can see that the numerator is actually divided by n minus k minus 1. So as k increases, what happens? As k increases, this denominator, whole thing, will go down. Sorry. I mean, as k increases, because I mean this n minus k minus 1 will go down, it means that this whole denominator will actually go up. And then this 1 minus thing kind of go down. So this R-square adjusted value is always less than R-square value. So why sometimes we have to use, I mean, we have to check the adjusted R-square value. If we put more values, I mean, if we add more values into this regression model, and then automatically R-square value will increase. But for this adjusted R-square value, because we kind of incorporate the number of variables in X, I mean, which is K. So if we put more and more X's, and then R-square value will kind of go down further. So if there's a big difference between R-square value and adjusted R-square value, then we can kind of guess that, oh, there are some variables that are not that much valuable, so we may have to get rid of those. Okay. Okay, so and then let's just see. I mean, how we can actually add an exploratory variable in radiant. So in this case, I mean, we are adding average snowfall. So when you add, I mean, snowfall, what happens is if you look at the R-scale value, well, this, I mean, the snowfall's coefficient, the p-value. The p-value is very large, 0.238. It means that the snowfall is not significant. And then R-square value has increased just by small amount, even though we have a new variable snowfall is added, right? So R-square has increased from 0.833 to 0.856, so there's a very small increase. So which also implied that snowfall is not significant. So at this point, I mean, we wonder, oh, what is meaning of this? I mean, this p-value. So what kind of hypothesis we are actually testing here? So let me actually explain a little bit. So this p-value is used to test the null is basically beta 4 because I mean beta 0, beta 1, beta 2, beta 3, and then beta 4. So beta 4 is 0. This is a null. And then alternative is basically beta 4 is different from 0. Because on p-value is 0.238, this is greater than 0.05. So we don't have enough evidence to reject the null hypothesis, which means that we still keep this one. It means that this snowfall is not impacting the sales. Okay. So, I mean, the kind of implication is that do not include unrelated variables just to fictitiously increase R-square value. Oh, and I think I've explained this in class. For this testing, we are going to use F statistic. And then you may wonder, okay, how this is made. So let me explain how this is made here. So F test stat is given by the difference between R-square value and also divided by number of new variables are added. Okay, we just look at this denominator thing. Okay, so if there is a lot of difference between R-square value normalized by number of new variables, then F value will be large enough to reject the null hypothesis. So if you get the null, we have the model y is equal to beta 0 plus beta 1 x1 and up to beta k1 times xk1. The alternative is that actually we have added xk1 plus 1, xk1 plus 2, and up to xk2. So basically we have added k2 minus k1 new variables. When you run the linear regression first, I mean, then we didn't specify this alternative hypothesis. I mean, if you look at this one, the alternative hypothesis we're testing is actually the effect of X on sales is not 0. So means that we're only testing that whether beta 1, beta 2, or beta 3 is different from 0, right? So in that case, what actually we use to calculate F is R-square value and divided by the number of X variables. So in this case, I mean, the null is basically, there's no X. So Y is equal to some constant plus some error. And then the alternative is that we have actually included X from the K2 variables. So from X1 and up to XK2. So simply speaking, if we have a large R-square value, then we tend to have large F. And that will actually give us enough reason to reject the null hypothesis. When you add some variables, the same thing. Considering the number of newly added variables, if there's enough increase in R square, then alpha will be large enough so that we are going to reject the null hypothesis. I mean, graphically, just for time being, let's think of the question, what if the regression line has zero slope? This is case basically, we don't use any x's or we don't have any significant x's. So if you look at the sales amount, the actual sales at, let's say, $1.2 billion advertising, this is the actual sales. This is the actual sales. So basically the YI, right? And then the average sales is here. This is the average sales. So the difference between these is total deviation. If the regression line has zero slope, it means that this is also same as the predicted value. So YI hat. So total deviation is the same as unexplained deviation error. So what happens is sum of squares total is the same sum of squares errors. It means that R square value will be basically the zero, right? So there's nothing that can be explained by this, X model, X variables. Again, in the left panel, you can check the some variables, and then if you specify these whole thing, then you can see that this F statistic, when you run the linear regression, we are going to see this value automatically, right? And the value that we see by checking the addition of these variables are basically the same. Okay. If we actually, another thing that you can recognize is that if we kind of check only one single variable addition, and then this F statistic has a relation with this t value. Because as you can see, these two p values are the same, right? And it turns out that if you actually square these t values, and it must be the same as this F statistic. So basically, using the p-value to find finding p-value is equivalent to finding p-value using this F statistic. So for the F distribution, if we specify 1 as the reason for why 1? Because we have added just one variable, right? And then we have a 10 degrees of freedom because we have a 15 observations, and the minus how many parameters we have estimated? We have estimated 5, right? So 15 minus 5, that's the 10. So 10 is the second degrees of freedom. And then this is the actual F distribution. And then for the 1.575, this is the rejection region, right? This is basically rejection region. And then we can easily see that this is pretty large enough, which is 0.238. So we cannot reject, but p-value is too large to reject the null hypothesis. We can actually check the these p-values by using the t-values. So basically, for the t distribution, we specify the degrees of freedom as 10. And so basically, the second degrees of freedom of F statistic goes to degrees of freedom for the t. And then, as you can see, because I mean for the t distribution now, then what we are testing is actually two-sided testing, right? Because I mean h no not is basically beta. In this case, beta 4 is different is 0, and the alternative is that beta 4 is different from 0. So the two-sided. So for the two-sided testing, um, if we have a 1.255 as the t-value, and then we can either compare this only one-sided area with half of alpha, or in terms of p-value, we have to double it. So why double it? Because I mean, this is two-sided, so either larger value, small value will give us the chance of rejecting the null or adopting the alternative hypothesis. So we have to double it, this area. And then as you can see, if we double it, 0.238. For only one area, this is 0.119. So when you multiply by 2, it'll be same as this 0.238. Okay? I think people actually, I mean, looking to standard deviation for the coefficients, let me actually show, I mean, this, how we can actually do this in radians, okay? Just to make sure that you understand what I'm doing here. So let's open the radiant, okay? So let's open your RStudio and then click, and let's start the radiant. So I think, I mean, I have already make the radiant started, and then let me actually have share that screen. So let's open the data set. So go to week 7, and then you can find the nature, right? So let's go to the basics, and then, oh, sorry, the model, and then linear regression, and then sales, and then let's say if we have including the snowfall, then the F statistic can be verified. It can be observed here. I mean, for the variables to test, if you click this one, and then you can select some of them out of these 4 variables. So if you, as I've explained, if you click only the snowfall, and then what happened is that basically the same F statistic we can see when you run the linear regression. So 14.828 for this one. I'm sorry. I mean the p-value. Oh, sorry. I think the to have the same 14.828, you actually have included all of these. Then you are going to have these the same F statistic. Okay. So basically, I mean, we compare 2 models. The first model, so this is kind of null, so there's nothing that explains sales. And the model 2, the bigger model, has actually have everything that we are testing here: advertising, promotion, computer sales, and snowball. Okay. Okay. And then if you want to look at only one variable, then as I explained, the p-value is the same as this p-value. Okay. So I think, I mean, the variable to test, this part is useful if you want to test not just one single variable. You want to test the addition of more than one variable, like including snowball and then computer sales, for instance. So when we actually, I mean, add these two, it turns out the p-value is 0.072. It means that not significant or marginally significant. It means that, and also, I mean, this computer sales is also marginally significant. And then it means that it's pretty obvious that some of the variable out of these two, so at least one variable is not significant, that is snowball, right? So we have to get rid of snowball, and then we run this linear regression model again. Okay. Or I mean, just as a as exercise, and actually include promotions, computer sales, only these two, then you can see that uh, what is interesting is that because I mean because of the oh, sorry, I mean I think I mean we have to include all of these, and then for this one, let's include only promotions and then computer sales. Then you can see that when you add these two, I square value has increased from 0.558 to 0.856. So there's a significant increase. So it means that this addition makes sense, and p-value is very little, right? Uh, oh, sorry, I mean not the snowball. I mean the promotions and the computer sales, right? Okay. So so that we can actually add, we can see that both two variables actually is significant. Okay. After I'm getting rid of the snowball. So this is how we can actually do for the variables to test. Let me actually go back to the slide. And then let's look at the standard deviations for the coefficients or the standard error. That's the STD error. And then t values actually just coming from coefficient divided by the standard error. So again, if this value is big, large enough, or small enough, then we are going to reject the null hypothesis. And the null is basically, for instance, for the advertising, the null hypothesis is basically beta 1 is 0, and then alternative is beta 1 is different from 0. Okay. For the promotions, the null is beta 2 is 0, and then alternative is beta 2 is different from 0. Okay. And then for the p-values, I mean, if we can see, I mean, these asterisk marks, and then these marks, and how many asterisk marks we are going to have depend on how significant the result is. So basically depending on the value of p-value. So if p-value is less than 0.001, then we have a 3 asterisk. Between 0.001 and 0.01, then 2. Between 1%, 5%, only 1. 5%, 10%, this period mark, or the, yes, this mark, anyway, mark. And then it's speaking, not significant or marginally significant. If it's over 10%, there's no mark. So again, p-value is the probability of finding such a t-value of this size if the null hypothesis is true. And also, if you check the confidence intervals, then you can see actually the confidence intervals of each uh each each actual coefficient value. I mean, as explained when you first start, the purpose of running this linear regression is to estimate the values for beta 0, beta 1, beta 2, and beta 3 in this case. So we don't know what these values are, so we are using these coefficients, right, to estimate them. But obviously, I mean, these are the point estimates, so they are different from the actual values of beta 0, beta 1, beta 2, beta 3. So we can actually check the confidence interval of these beta i's. So for instance, for the advertising, so beta 1, right? So beta 1 will be between these two values with 95% probability. So beta 2 will be between these two values, again with 95% probability. Beta 3 will be between these two values with 95% probability. So, I mean, these confidence interval also give us the same result that is based on the p-value, right? Because, I mean, think about it. These two intervals do not include 0. It means that beta 1 must be different from 0, beta 2 must be different from 0, with 95% confidence. Similarly, this interval does not include 0, so we can conclude that beta 3 is different from 0 with 95% confidence. Okay? So, I mean, whenever this confidence does not include the 0, basically that beta I is significant, right? I mean, the X variable is significant. And then we can actually, I mean, you can look at the plots, and then you can see that all these actually does not include the 0. Okay, I think, I mean, that's pretty much about it about the linear regression that actually has started last time. So this is basically the linear regression, the part 1. And then in part 2, we are going to look at the some aspects, some more details regarding the linear regression using how we can actually check the models and etc. Okay. Okay, thank you for watching.